Hello, everyone. Today, I will be presenting the research titled E2EGS, Event-to-Edge Gaussian Splatting for Pose-Free 3D Reconstruction. Let's begin. Let's start with the background. The advent of neural radiance fields and 3D Gaussian splatting has revolutionized the field of novel view synthesis. However, despite their remarkable success, these approaches fundamentally assume high-quality input images and require accurately estimated camera poses. This makes them highly vulnerable to real-world challenges, such as motion blur and adverse lighting conditions, which frequently occur during rapid camera movements or in low-light environments. To address these limitations, we focus on event cameras. They offer exceptional temporal resolution and a high dynamic range, making them highly effective at handling motion blur and poor lighting. More importantly, because they detect pixel-level brightness changes, event cameras naturally generate dense responses at edges and texture boundaries. This provides rich structural information about the scene geometry, which is why integrating event streams with 3D-GS frameworks has recently gained significant attention. A notable related work in this field is E2EGS. It adopts SLAM principles to perform pose-free 3D reconstruction by iteratively optimizing both camera poses and 3D Gaussians. While it represents a significant step forward, it relies heavily on pre-trained monocular depth estimation models, like Marigold, for its initialization. When the depth model fails, or when the camera explores new spatial regions beyond its initial observations, the method's performance degrades drastically. To overcome this, we propose E2EGS, a framework that operates solely on event streams without any reliance on depth models. Our pipeline consists of three main steps. First, we extract robust edges from consecutive event maps through temporal coherence analysis. Second, we use these edge maps to initialize edge-aware 3D Gaussians. Finally, we apply edge-guided losses during the joint optimization of the 3D scene representation and the camera trajectory. The first key module is robust edge detection via patch-based temporal coherence analysis. When a camera moves, true structural edges produce correlated event responses, while non-edge regions generate sparse, random noise. By analyzing the variance of the temporal difference signal across consecutive patches and applying an adaptive threshold, we can robustly extract strong edge responses. A post-processing step involving Gaussian smoothing and morphological closing gives us our final, clean edge map. Next is the edge-guided Gaussian initialization. First, we extract 2D edge points and their normal directions, applying a recursive grid-based subdivision to create 2D edge Gaussians with highly consistent orientations, as detailed in Algorithm 1. Then, as shown in Algorithm 2, we lift these 2D Gaussians into 3D using inverse depth sampling along the viewing rays. This strategically allocates more points at farther distances to improve rotational observability for pose estimation, while also adding random Gaussians to fill in textureless surfaces. During the joint optimization phase, we perform edge-guided 3D reconstruction. We introduce an edge-guided loss function that spatially weights the photometric reconstruction error based on the edge confidence map. Combined with a structural dissimilarity loss, SSIM, this ensures that our optimization process prioritizes geometrically salient boundaries over noisy, uniform regions. Moving to our quantitative results. In Table 1, evaluating on the synthetic replica dataset, E2EGS achieves the highest NVS reconstruction quality using only event data. Furthermore, Table 2 shows our superior trajectory estimation accuracy. We outperform state-of-the-art baselines like DEVO, ESVO2, and E2EGS without depth priors. As you can see in the graph, Figure 2, our edge constraints ensure that the trajectory error remains consistently low, even as the sequence length increases. Here are the qualitative results on the replica dataset. If you look at the red boxes, baseline methods like E2EGS exhibit wave-like artifacts and miss fine details. Without depth initialization, E2EGS fails completely due to severe trajectory drift. In contrast, our E2EGS prioritizes geometric structures, resulting in much sharper boundaries and cleaner surfaces. This slide highlights the impact of trajectory error on real-world sequences from the E2EGS dataset. E2EGS suffers from spatial misalignment, viewpoint shifts, and blurry or disappearing objects when the camera explores regions beyond its initial coverage. Our method, however, maintains accurate spatial alignment and sharp textures throughout the sequence by leveraging robust edge information. We also conducted ablation studies to validate our components. Table 3 confirms that using both edge initialization and edge loss minimizes the absolute trajectory error, ATE, most effectively. Table 4 and Figure 6 analyze the edge ratio parameter. If the ratio is 0, fine details are lost. If the ratio is too high, smooth surfaces are underrepresented, leading to poor trajectory estimation. A moderate ratio between 0.1 and 0.3 provided the optimal balance of detail preservation and trajectory accuracy. This is a rendering video from the E2EGS 3D sequence. As you can see, even under complex camera motions, E2EGS stably reconstructs the 3D scene geometry purely from the event stream. It does so entirely pose-free, without relying on any external pose tracking. In conclusion, E2EGS establishes a fully pose-free paradigm for event-based 3D. In conclusion, E2EGS establishes a fully pose-free paradigm for event-based 3D reconstruction. By explicitly extracting and utilizing geometric edge cues from event streams, we achieve superior trajectory accuracy and high-quality scene reconstruction, completely eliminating the dependency on pre-trained depth.